Okay, so we've talked about parabolas, we've talked about ellipses, and today is Hyperbola Day. Remember, we learned that an ellipse has an eccentricity somewhere between 0 and 1. The greater the eccentricity, the more elongated and non-circular the ellipse is. If you let the eccentricity go all the way to 1, then the ellipse sort of opens out into a parabola. In a way, you can think of a parabola as being like an ellipse that sort of stretches infinitely far. It's one end of an infinitely long ellipse. If you keep on increasing the eccentricity past 1 to numbers like 1.2, 1.4, 1.6, 1.8, 2, 2.1, and so on, you get a curve like this that is a hyperbola. And notice it's made up of these two branches. So these two together make up the hyperbola. And there are two ways you could define a hyperbola, two alternative definitions. The first would be the exact same definition I gave you last time for an ellipse, but instead of the eccentricity being less than 1, the eccentricity is greater than 1. So you start with a point for the focus and a line for the directrix, and then the hyperbola is made up of all points whose distance from that point to the focus is equal to e times the distance from that point to the directrix. If that number e were less than 1, that would give you an ellipse. If e were equal to 1, that would give you a parabola. And if e is greater than 1, that gives you a hyperbola. The other alternative definition, the other way of defining a hyperbola, is to start with 2 points to be the foci and a fixed positive number, and then take all points so that the distance from one point to the focus, from that point to one focus, minus the distance from that point to the other focus is that specific number, 2a. If this were a plus instead of a minus, we'd have an ellipse. That was the other definition we saw for an ellipse, where the distance from one point to a focus plus the distance from that point to the other focus was constant. So if the sum is constant, you have an ellipse. If the difference is constant, you have a hyperbola. An ellipse, here's an example of an ellipse, x squared plus 20, or x squared over 25 plus y squared over 16 equals 1. If we keep that equation almost the same, but change that plus to a minus, we get a hyperbola. So a hyperbola, in a way, it looks like we took the ellipse and we turned it inside out. So instead of starting at the vertices and coming inward, you start at the vertices and go outward, and you get the hyperbola. So this right here is x squared over 25 minus y squared over 16 equals 1. That's what the graph looks like. If we put the y part first in the subtraction, with ellipses, we're adding, so the order doesn't matter. If I wrote it with the y part first, y squared over 16 plus x squared over 25 equals 1, it wouldn't change anything. It would still be the same ellipse. But with subtraction, of course, the order does matter. So if I put the y part first here, y squared over 16 minus x squared over 25 equals 1, we get this kind of hyperbola. So instead of the branches going out to the sides, the branches go up and down like this. Now take a look at what's going on with this hyperbola. If x in this equation is 0, if we put 0 in for x, then we just get y squared over 16 minus 0 equals 1. And the only way that can happen is if y squared is 16, which is when y is either positive or negative 4. So that gives us the points 0, 4, and 0, negative 4 on the hyperbola. If we put 0 in for y, we get 0 minus x squared over 25 equals 1, or just negative x squared over 25 equals 1. And for that to happen, x squared would have to equal negative 25, which is impossible if x is a real number, which are the only things that show up on the graph. So there are no points on the graph that have a y coordinate of 0. In fact, there are no points on the graph that have any y coordinates anywhere between negative and positive 4. That's because if you rearrange the equation a little, it says y squared over 16 equals 1 plus x squared over 25. And that x squared over 25 part, because it's something squared, it can't be negative. It's got to be 0 or bigger. So 1 plus something that's 0 or bigger has to be greater than or equal to 1. So since y squared over 16 is greater than or equal to 1, y squared must be greater than or equal to 16. If y is a positive number, that means it has to be greater than or equal to 4. Or y could be a negative number that's less than or equal to negative 4. Now, if we took this hyperbola here, this y squared over 16 minus x squared over 25 equals 1, and replace y with y minus 1, and replace x with x minus 3, then that just shifts everything over 1 space in the y direction and 3 spaces in the x direction. So all the points have been shifted 3 spaces right and 1 space up. The point that used to be at 0, 4 is now over at 3, 5, for example. And the point 0, 0 that used to be kind of right in the center of this hyperbola, now the point that's right in the center of the hyperbola is at 3, 1. So let's look at what's going on with this hyperbola. Like I said, the center, that's the point that's right in the middle, halfway between the two branches. That is 3, 1. It's a point where x is 3 and y is 1. The vertices, so those are like the turning points on the two branches, the points on each branch that are closest to the center point. So one of them is up here at 3, 5, and the other one is down here at 3, negative 3. So they are 4 spaces above and 4 spaces below the center. So we use the letter A to stand for the distance from the center to either one of the vertices. And where that comes from in the equation is that the number in the denominator of the first term here is a squared. So here a squared is 16, so a is 4, and that's how far you have to go from the center to get to either one of the vertices. In this case, it would be in the y direction, because it's the y term that has the a squared under it that comes first in the subtraction. And if we draw a line connecting those two vertices, that's called the transverse axis of the hyperbola. So it goes across, it transverses or goes across this no man's land in between the branches, from one vertex through the center to the other vertex. So the total length of that transverse axis is 2 times a, which for this particular hyperbola is 8. Then the conjugate axis is perpendicular to the transverse axis. If we draw a line segment through the center in the other direction from the way the transverse axis was going, that is what we call the conjugate axis. And it has a length of 2b, where b squared is the number in the denominator of the second fraction. Here, b squared is 25, so b would be 5. So the conjugate axis is what you get if you start in the center and go 5 spaces one way and 5 spaces the other. In this case, in the x direction. Now, if you draw a box or a rectangle around the transverse and conjugate axes, like this, and then you draw diagonal lines that go through the corners of that rectangle, and they cross in the center, those diagonal lines are asymptotes for the hyperbola. That means that the hyperbola itself will never quite touch those asymptotes, but it will get closer and closer to them. So if you zoom way out, the parts of the hyperbola that go way out there are getting closer and closer to these straight diagonal lines. The foci of a hyperbola are out past the vertices on the inside of the curves. They are c units away from the center point in the direction of the transverse axis, where c squared is equal to a squared plus b squared. For this particular hyperbola, c squared would be 16 plus 25, or 41. So c would be the square root of 41, which is approximately 6.4. So to get to the foci, you could start at the center point and go up about 6.4 spaces to get one of them, and go down about 6.4 spaces to get to the other focus. So with a hyperbola, unlike with an ellipse, the foci are farther away from the center than the vertices are. That means C is greater than A. So when we were talking about ellipses, we had A squared equal to B squared plus C squared. A was the biggest one of those three numbers. When we're talking about hyperbolas, we have C squared equal to A squared plus B squared. C is the biggest of those three numbers for a hyperbola. So a hyperbola can go either direction. It can have a horizontal transverse axis or a vertical transverse axis. The way you tell, it depends on which part comes first in the subtraction. If the x part comes first, the transverse axis is horizontal. It goes in the x direction. If the y part comes first in the subtraction, the transverse axis is vertical. It goes up and down in the y direction. So the equation for a hyperbola looks like one of these, depending on whether the transverse axis is horizontal or vertical. Unlike with an ellipse, A is not necessarily greater than B. When we were talking about ellipses, we said that A was the bigger one of these two numbers. With hyperbolas, A is whichever one comes first in the subtraction, but it might or might not be bigger than B. So in any case, HK is the center of the hyperbola. The vertex are points on the hyperbola, A units away from the center point, along the transverse axis. The length of the transverse axis is 2 times A. The length of the conjugate axis is 2 times B. If you draw a rectangle enclosing those two axes, the diagonal lines passing through the corners of the rectangle and crossing in the center are the asymptotes of the hyperbola. And each focus is a point inside one of the branches of the hyperbola, C units away from the center, where C squared equals A squared plus B squared. And for a hyperbola, the eccentricity is C over A, C divided by A. That's exactly the same formula as the eccentricity of an ellipse. But with an ellipse, C is smaller than A, and that gives you a number less than 1. For a hyperbola, C is greater than A, and so that gives you an eccentricity greater than 1. Okay, I'll be back in part 2 with some specific examples that we worked through.